All right, how we doing, everybody? Doing good? Wow, we only have a few people here. Is it the festive week, or was it exams?
No, because the exam at least for Pushkin was on Monday. So today we just talked about capacitors barely, so that's probably why not likely to come.
Okay, so Q is equal CV. So we're finally talking about capacitors. Have we talked about inductors yet? No.
We mentioned it, but didn't go fully by. So opportunity is a brief introduction.
All right, so I'll just give you guys my practical just so you guys can get your homeworks done. So anyways, so they've introduced you to our little fella, right? Just the capacitor, right? Does that make sense? Where this capacitor is going to have some, I don't know, I'm just going to guess it, some type of area, right? It's going to have some type of size. Sometimes some, I don't know, some dielectric constant. I call this like, I don't know, the jelly filling of your actual capacitor, right? So if it's like if it's a quality material, right, capacity goes up. Does that make sense? Correct? And then divide it by some distance for the plates, all right? I'm just talking about bare physics, okay? So everyone knows that this right here is our distance here, and then this right here, I'm just gonna make it, I don't know, blue. There we go, dot, 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 dot. That's right here is our material, our dielectric, whatever is in that material, right? And then our area itself is gonna be, what do you call it? If I were to draw the area, right, the area of the plates, if I were to draw like two squares, correct? This is the area of a plate, right? And then in between that, I have this material, it's a sandwich, okay? All right, and how do I increase the capacitance? Just look up at the distance, okay? Has everyone understood from our physics classes what a capacitor is? Have you guys seen a capacitor? No? Let me see. Capacitors, well, they look like this. Let me show you. I'll show you that later. Capacitors. They look like these little funny guys right here. Little storage tanks. Parallel plate capacitor. Stuff like this. I don't know if there's a real life version. You see, oh yeah, this is a good example. See those two right there? It's two plates. You got the area, well, area of a circle. Not that hard, right? These are circle capacitors. I don't think there's any other good examples, but it's literally that. That's not that bad, okay? Anyways, what's the other thing we knew about capacitors? Anybody know? There's going to be some associated charge, right? We're going to put some type of like, we're going to fill this capacitor with some charge, correct? And there's going to be some voltage. Is that good? Or another way to rewrite this, Q is equal to CV. Remember that? What's Q? Charge, right? In coulombs. Coulombs, right? Or C, or not. If I put C, it's not gonna be the right answer. But you know this is coulombs, all right? Then this is our actual capacitor in farads, all right? And that's just our voltage right here. Okay? Everyone understood what's going on with capacitors? Just really basic stuff, okay? So what's the other thing that they talked about with capacitors? For Dr. Zhu's class, do we have any of you guys here? No one from Dr. Zhu's class? No? Uh-oh. Oh, one? What are you guys going over? Oh, you don't know? I'll have to figure that out, because thank you for the Pushkin students coming in and bringing me your feedback, but I need to know what's going on with Zhu's class, okay? But anyways, I'll just go over my gist of what I'm going to try and do, so. Yes?
Pulse, step, exponential. There was one more?
Currents?
That's just a bit more.
Yeah, I'll show you something simple.
Unit step and stuff like that.
Unit step functions. Oh, those are all mathematicals. Okay, I'll explain it because I also do signals and systems at the university here. Let's just say I have some, I don't know, value, voltage, correct? And this is time, correct? And if I have at 0, right, it's steps, correct? Unit step is defined by some U, 1 volt. Right? How do I mimic this in LTSpice? Plus, minus. Using a switch, right? Correct? So if this is 1 volt, correct? What's the voltage over here when this is opened? 0, right? But now I finally close that puppy, right? Bang, boom, it's closed, right? What's the voltage over here? Turns to 1 volt, all right? If I did it at t is equal to 0, right? Boom, now we just went up. Does that make sense what a unit step is? And then you guys said there's a ramp function. How do I want to generate that one? Well, there's one way to generate that. Plus, minus. And you just have it from 0 to 1. So you have to generate a ramp function. And, okay, I guess I can show you this. Where initially this is going to be 0, and it's going to go up to 1 volt, right? 0 to 1 volt. Guys, I'll show you guys how to generate these signals so you guys know what's going on, all right? And then the square pulse, well, there's many ways to do a square pulse. You can use a switch, or you can just use LTSpice's switch from -1 to 1 volt resistor. And then you start seeing that this goes to -1 to 1 volt. Does that make sense? Yeah, just simple mathematics, okay? Is that good with everybody? Just the bare bone basics? Okay, I think everyone wants examples. LTSpice. Boom. Save as 220. Let's see, week 10. Hooray. You guys excited we're on week 10? I think we only have like 6 more weeks. 6? Yeah, 6 more weeks. And then this is going to be called EE220D LEC, I don't know, 10, EX1, example 1. I guess that's what I'm calling it. Where I have this voltage source, right? Resistor. We're just going over some bare basics, okay? No, okay, I'm just going to I'm going to go over the hard way. Okay. And then I'm going to create some text. Comment. Okay. I press this button. There's these two guys right here. Text and Spice directive. I'm going to press this blue text right here. I'm going to call it ramp function. Okay. What do you guys want the ramp function to do? Just go 1 volt every second? Is that good? So if I were to do the following, let me just go back to our thing. Oh, open the multiverse right there, okay? Just consistency. I'm going to go 1 volt, right? Every 1 second, correct? Then my line's going to look like this, right? Is that what I want to generate? And then I just keep going up to whenever I want it to be. Is that good? So let me see. Oh, I think I know a good example we can try to do. If I go right click and go to advance, all right? And let me just do a pulse, because a pulse you can do ramps. You can also do some other fun stuff, but I'll show you guys with the pulse function. The pulse function you can create square waves, triangle waves, whatever you want. So what do you guys want? It's going to start at 0 volts, right? And I'm going to make it on, what do you want it? I think I'm going to go up to, I don't know, 10 volts, right? Delay just means how long do I want to delay, no delay, okay? And then rise, this is what matters. How long does it take to go up? So it's going to be based on these two right here. So let me see. If I'm going from 0 to 10, and I'm rising, all right? In 10 seconds, right? I want to be at 10 volts, right? So let me do one more thing. Okay. Visualizer. What's the slope? It's going to be rise over run, right? We're rising up by 1 volt, right? Per 1 second, correct? At the end, right, I have this thing, final voltage of 10 volts, right? And then I have, I don't know, X seconds, correct? Is equal to 1 volt over 1 second. Solve for X. What is X equal to? 10 seconds, correct? Does that make sense? Anyways, let me just go back to our little guy here. So that means we're gonna rise in 10 seconds, correct? And then fall time, I'll just fall down by 10. T on, I'm gonna put 1 microsecond. So I'll tell you this, why I'm doing 1 micro, something very tiny. Because I just want it to be a ramp. If I have some, I'll show you what I mean. 1 second. And then period, nothing. Boom. All right, I call this one V out. And let's run this guy. I'm gonna do 20-second run. Can't find the model of R. R is gonna equal to 1K. Easy. Then let me just stretch this so we can see. Boom. Does that make sense right there? Let me just zoom in right here. Go from 1 volt, let me see, 0 to 2 volts with a 0.5 tick. And then I'm gonna go to 2 seconds. Is that cool? 1 volt over 1 second. That's what this guy's seeing if I were to do this. Easy stuff. And then let me just do the full picture. Zoom to fit. Look at that right there. I have a 1 second hold. That's why I was trying to do this. T on for like 1 microsecond. So now it looks like a triangle wave. Is that cool? Any questions about that? Yes, no, maybe? Okay, I'll show you guys another thing because I think this is more important too. Ramp function, yeah. Save as example 2. Okay. And remember that time I talked to you guys about a switch? Let me bring that back up here. So I'm going to delete this. I'm going to press P for component, switch, SW, right? Remember this little guy? No, man, we hated it. There we go. Now I can do this V in. And then I'm going to do none. Do 5 volts. Right? And this is going to get you guys introduced to capacitors. So I'm going to build something right here. I'm going to build a little switch right here. And boom, boom, boom. Boom, boom, boom. And this one's going to be V switch, correct? I'm going to have this switch turn on right here. All right? And I'm going to put it at 0 volt reference. Zoom to fit. Come on. Zoom area, zoom to fit, space button. Is that good with everybody? I'm going to make this, what do you call it? Oh, yeah. So the other thing about this is you got to create a model. Dot model. My switch of the class SW R on. On resistance is going to be very tiny. R off is equal to 1 meg. There we go. And then VT, I think VTO. Yeah, I'll figure that out. There we go. So now someone's wondering, why did I do my switch? So if I go over here, our value right here is my switch. Okay? Everyone following? So now I'm going to do a following. We're here. I do need a pulse this guy right here. Pulse. I'm going to go from 0 to 1 with a 1 second delay. Very small, very fast rise time, very fast fall time. All right. On for, I don't know, 5 seconds. Is that good? And now there's another thing I got to look up. LTSpice switch model parameters. Okay. You see, there's a parameter in here. V. Oh, there it is. VT. There you go. V threshold. That's what I want to change. So I'm gonna make this as easy as I can, okay, for everyone to understand. Is everyone cool with 0 volts, like the switch is off, and 1 volt, the switch is on, we're powering it on? Yeah, in other classes, some people are taught that anything above 0 volts, so 0.11 or 0.001 is on. So that means you have to put a negative voltage. That's fine. It's whatever makes sense for you, okay? So I'm going to change this V threshold, right? V threshold, VT, as 0.5 volts, just halfway, okay? Like that? I'm going to run this. Boom. Is that cool? I'm going to look at V switch, right? We turn on at half a second or 1 second, right? And then, what's his name? What's VN? VN is just 5 volts, okay? And this is my switch, correct? It just turns on, right? This is already a short. At this point, it's a short, correct? So that means when this is on, right? What's V out? 5 volts. Nice, right? You like that? Simple stuff. So this is gonna help you guys with your homework. You guys are gonna be doing some capacitors, and you guys are gonna see switching. Open the switch, close the switch. Let me just Control S. You guys can use this as a reference. Anyways, let me show you another thing before I move on to something even crazier, because I need everyone to know this. Page 2. Page 3. So, are we all familiar with the following equation? There we go. For a capacitor. Equals C dV over dt. You guys seen that? Right? Nothing too crazy, right? So I'm going to do the following. I'm going to throw some, I don't know. I'm going to throw this with a, what do you call it? I'm going to draw it like this. I'm going to fill this bucket of water. Okay? There's a current I, right? And then I'm going to have some V out. Is that good? All right. And let me just see. Plus, minus. And that's the current that's going in. All right. So there's another way you can rewrite this with a constant current source. Is you can rewrite this as dV over dt is equal to I over C. What did that tell you? I'll show you. So it's time equals 0, correct? After, I don't know, time is equal to 1 second, correct? What's the voltage? All right, let's just draw this out, okay? This is my voltage, right? V out, correct? This is my time, correct? This is 1 second. What's the voltage? All right, so let's see. What do we know? I'm going to put 1 amp, right? 1 amp into that circuit. Cool. And then let's just say I put, I don't know, 1 microfarad, all right? Everyone knows what a microfarad is? No? So basically it's, if I have micro, which equals 10 to the minus 6th power, correct? Then I have nano, right? This is equal to 10 to the minus 9th. Is that making sense? Or if I wanted to go, I don't know, K for kilo, right? 10 to the 3rd. All right, we're going to use microfarads a lot for all your circuit designs. So what's his name? 1 microfarad, that's just 10 to the minus 6 farads. All right, just a value. All right. So I have I, correct? And I have C, correct? 1 amp, right, over 1 microfarad, correct? Which is equal to dV over dt. So what does this tell you? I feel like I want to show you everyone what's going on. So let me see. dV, right, it's a change of voltage, right? And dt is a change of time, right? But can you tell me with this equal sign what I can relate this 1 amp and this 1 dV, or this change of voltage? What does this mean? Anyone clicking? Let me show you this. So if I have a change in voltage, right? I'm changing voltage, correct? dV, right? And I have a change in time, correct? What does that tell me about my slope? I'm going to go up 1, right? 1, right? 1 amp rise over, well, this is not 1 second. This is going to be 1, what do you call it? 1 UF. This is supposed to be 1 UF. 1 microsecond. There we go. Does everyone see what I'm trying to do right here? So if I'm changing if I have 1 amp over 1 microfarad, right? What does that tell me about my voltage and time? 1 volt over 1 microsecond. Does that make sense? You guys want to see a proof? Let's do it. Example 2. Let's create another one. Save as. Okay. Oh, come on. Just do the following. There we go. Let me see. Control S, Control S, Control S. Has anyone had an issue where LTSpice was rewriting some stuff? Save as. Exercise 3. Do the following. Delete. Yeah, let's just delete the whole thing. Capacitor. So you press C for capacitor, or you can go to components by P, capacitor, cap. Was that cap or no cap? Current. Oh, cur. There we go. Boom, boom. Oh, oh. Yeah, just leave that there. Boom, boom. I'm going to put 1 amp. All right. And I'm going to put 1 UF for 1 microfarad. Put V out. All right. I'm going to run this for, I don't know, 10 microseconds. Okay. What happened? Let's see. Node V out is floating. 1 amp. Huh. What happened here? Now let's run this one. Node N1 is floating and connected to current source 1. Huh. Wait a second. Wait a second. 1 amp. 1 microfarad. Don't tell me you need to put a series resistor in here. Equivalent series resistance, I don't know, 0.001. Node N1 is floating. What? Hold up, hold up. View, zoom to fit. What's going on? Let me check. Do my sanity check. 1K. See, that runs, okay? I want to show you this. Capacitor, boom, boom. 1 microfarad. Maybe it doesn't like the U. Node N1 is floating and connected to the source. No, I think .IC. I think I know what's going on. V out. dot IC initial condition V of V out is equal to 0. Let's see if this works. And then, let me edit this. Skip initial operating point solution. Let's try that. There we go, it ran. Okay, 1 amp. There you go. Does that make sense? Let's see if you guys understood what's going on. Let me just double click on this. I'm gonna go from, I don't know, 2, and then I'm gonna do 2 volts over here. 1 volt, 1 microsecond. Is that cool with everybody? So what I did right here was I had to force it. So basically what LTSpice was saying, okay, let's get rid of this, okay, just to understand what's going on. Okay, I understand what's going on. So capacitors are magic little guys, and they hold buckets of water. And LTSpice said, well, what magic number is it going to hold? So it doesn't like it when we let it think. And if we force a number, so I'm saying, hey, the voltage here is a guaranteed 0 volts, okay? Because capacitors only give you current, or these current supplies only give you current, but doesn't give you a certain voltage, because there's no resistor here, right? How do I generate a voltage? There's got to be a resistance, correct? But there isn't you don't see no voltage drops, right? So anyways, I had to force this to be 0 so that now this current supply knows what to do. Okay, now I can just throw one amp into this, all right? 1 volt, correct? Let me just see, Control Z. Yeah, but does everyone see what I just did right there? Cool. Anyways, let's see. What's the other thing they taught you? Let me see. I'll give you this simulation to run that. Did they actually tell you what else to do with the capacitor or not yet? What else have you talked about? Have they taught you how to actually put it in your circuit?
No.
Not yet? You guys want me to touch on that a little bit? All right, so I'll show you what I mean. So if I were to do the following, let's just say capacitor. Let's put a resistor here. I don't know, I'm just creating some numbers. And let's just say, oh, I should probably have drawn this differently. Supply in here, V initial is equal to 5 volts, all right? That makes sense for everybody? I'm gonna do plus minus, right? I, and there's some resistance R. Is everyone getting what I'm doing? And then there's some capacitor C. Cool. Let me see if this is a better way to teach it. Yeah. But most of your circuits are gonna be in some format like this, where you're gonna have a switch, it's open from T is less than 0, right? And then closed at T is equal to 0 and beyond, right? So before, right, it's 5 volts, correct? We have 5 volts in this. Does everyone understand what I'm trying to say with this capacitor, right? If I were to do a capacitor, right, and it's got some water in it, right, it's a glass of water, and the glass of water is, I don't know, half full, right? And then I have, I don't know, some guy with a straw. I don't know. Straw. And then, I don't know, he's just happy. Drinking the water, right? The water flow from this is like, I don't know, I'm going to drink like 1 sip per 1 second, right? And you're going to notice that once I close this switch, I'm going to start draining that water, right? So initially there's some water in there, right? Now I'm about to drink this water, okay? Make sense? Okay? So what's the next thing I got to do? So if I were to do this, correct? Let me see how I want to show you. I did this circle right here, this current, right? Plus minus, right? Plus minus. Is anyone confused why I did plus minus, right? So I'm drawing my current, correct? That's step one. Step two is plus minus. For resistors, it's going to look like this. V is equal to IR, right? And then for the capacitor, right? Well, I don't want to spoil the surprise. Yeah, okay, so there's I, which is equal to C dV over dt, correct? And then if I wanted to solve for, what do you call it? This actual function, let me show you. Let me see. I over C dt is equal to dV, right? And if I do an integral, correct? Then you'll realize that V out, actually, let me see. V in, V out minus V in. Let's just assume that's 0. It's equal to integral of I in terms of t dt 1 over c. Does that make sense? Actually, this is dv out. Yeah, v out minus vi. Some type of format like this, okay? Is that good with everybody? So that's why I'm trying to do it like this, but this is much easier to understand. I'll show you what's going on. So the voltage of this capacitor, right? VC, I'll use a different marker. V cap, correct? It's going to be V plus minus V minus, right? But I need to know that dV, correct? So this is going to be my plus, and this is going to be my minus, so I can get this equation. All right? That makes sense with everybody? So if I were to do a KVL going from here to here, so let me see. Start right here. I'm going to run. I'm going to go down the hill, correct? Minus I over R, right? Then I'm going to go down the hill. VC, correct? What's VC? V cap plus minus V minus, right? Which is equal to 0 minus V out, right? Cool for everybody? Is that good? Minus IR is equal to VC, which is also equal to minus V out. Is everyone following what I'm doing? But then there's another thing. Let me show you. Is remember this I is equal to CV over CdV over dt? That's that current right there, okay? The current, this current that's going in the circuit is being dominated by this new equation that we have here, I equals C dV over dt, okay? Is everyone following what I'm trying to do? And let me show you on a new piece of paper. This is page 3, this is page 4. Because I knew when I did this, when I was an undergrad, I had a hard time understanding it too. 5. Just do this again. Minus IR, right, is equal to minus V out, right? Does anyone bother if I just do plus and plus? Simple as that. And then remember that I is equal to C dV over dt. Is that cool? So I'm going to plunge this guy right in here. C dV over dt. But then there's this R term right there, right? Is equal to V out. Is that good? But this V right here, this is actually VC, okay? That's the voltage change in that capacitor. So dVC, right, is basically D, what do you call it? VP minus VM, V plus minus V minus, right? Which is equal to dV out. Is that understood with everybody? What I'm trying to do? Let me just go over this one more time. So the cap, right? There's going to be a voltage, right? V plus minus V minus, right? All right? And this is the voltage that we're going to be using in our I equals C dV over dt, correct? Because we want to know the change in voltage, right? V plus minus V minus, right, was equal to 0 minus V out. Is that understood? I'll just put this guy over here. All right, D minus V out, okay? So if I'm looking just at that term, and I'm trying to plug this guy back in there, I'm going to get minus RC dV out over dt. V out. Looking good? All right. So now the next thing I'm going to have to do is I'm going to have to put separate all the variables. So I'm going to do the following. Let me see. I'm going to move this V out over here. So I'm going to have dV out, okay, over 1 over V out is equal to minus 1 over RC dt. All right. Now I'm going to do an integral. Everybody remember the integral of 1 over x with respect to x, or dx? Remember this one? 1 over x dx. Remember that guy? Is equal to ln of x. Right? Calculus. Whew. So this is going to transform into ln of v out, okay? Now let me see. Okay, let's do this. ln of v out. But let's just say we have some v initial, correct? And this is v out or something like that. Okay? When I have some initial voltage at that capacitor, I'm going to get ln of v some initial value, correct? That's just for completeness, minus from a to b of the integral is equal to, if I were to integrate this, right, 1 over RC times t. Is that good? Just going to go from 0 to t to make it simpler, okay? All right. And then you guys remember what the properties for when you're subtracting natural logs? You got this one right here. Let me, where do I want to write this? Now I'm going to skip steps. ln v out over v initial. Remember that? The subtraction right here turns into this 1 over a over b, right? Minus t over rc. We're getting close, right? You guys feeling it? Okay. So let me rewrite that right here. ln of v out, vi, good, minus t over rc. All right. I don't like this ln. I want to get rid of it. All right. We're going to put an exponential. Put an exponential. All right. We're getting there. So then what's going to happen? Well, this e and this ln cancel out, correct? So that means we're going to get v out over vi is equal to e minus t rc. All right. Now what do we have left over? This is going to be the equation that's going to haunt you forever. Like that? Whew. It's your proof for the capacitor, discharging capacitor. Does that make sense? You guys want to see this in action? I don't know. Let's just do something funny. So let's just say I have this capacitor, right? And I'm going to put 5 volts in it, right? And I have some R, correct? I don't know, it's going to be like 1K, correct? And this is 1 microfarad, correct? What's V out after if I close this switch right here? It's dominated by this equation, okay? All right, let's think about something quickly, okay? I'm going to draw this again. Okay, it's not connected, 5 volts, right? So if I were to use this equation, right, V out at 0, right, time is equal to 0, right, t is equal to 0, correct? What happens to this equation? Well, what's our initial voltage? Initial voltage is 5 volts, right? 5 volts, e to the minus 0 over RC. What happens when you have e to the 0? turns to 1, right? Is that good? Is that making sense? The math does, but what about the engineering? All right, we'll get you there. But you know that, okay, let's just do t is equal to 1 second, correct? Now 1 second just went down, right? So I'm going to do V out of t is equal to 1 second, right? Is equal to 5 volts, e to the minus 1 over RC. What's the voltage there? Whatever this computes. Punch that in MATLAB or calculator or whatever. Is that making sense? All right, let's just do an example. Don't want to lose you guys. Save as. We're running out of time too. Well, not really. Just getting started. Let me just do this. I'm gonna get rid of this. Boom, boom. Put a resistor here. Do your professors do this in class? No? You wish they did? It does take time, but I'm just trying to get you guys solutions, okay? Yeah, because I think when I did this class, we didn't even have discussions. In fact, we just did everything. Like everything I'm doing here, an hour and 45 minutes. Wait, is that how long classes are? Hour 15. Man, I wish I had an extra 15 minutes. Anyways. V out, right? I'm going to set this. Actually, let me just do something funny so we can replicate the actual problem. I'm going to open up example. Was it example 2? Yeah, there we go. I'm going to copy paste this pulse, okay? I'm going to copy paste this guy right here, okay? Guys like that? We're reusing stuff. I'm going to connect this guy there. So it looks just like that switch, all right? So I'm going to put, what do you call it? V in, right? That's my V initial, right? V final, okay? And my V initial, I'm going to do this. Dot IC, the voltage of V initial is equal to 5 volts, okay? Everyone's good with that? And then I'm going to do something just for my sanity check. I'm going to copy paste this. What did we say about the initial, or what do you call it? The voltage right here at t is equal to 0, like right before the switch opens? 0, right? So I'm going to do the following. What the heck? There we go. V final, okay? Or actually not V final. I'm just going to do, I don't like V final. V out. There you go. V out. Boom. And this one, I'm going to force it to 0, okay? Just to make sure everyone's happy. All right? So let's see. Our transient, I think it's going to run too fast. I'll show you what I mean. Let's run. I'm going to do it for 10 milliseconds. Oh, what did I forget? Open. Forgot the model. Our switch that we just invented. Is that good with everybody? Let's run this. Actually, before I run this, let me see. T delay, T rise, T fall, we're on. Okay, cool. We're going down. I don't like that. Okay, I think I know what's going on. Let me just see. 0, 0, 0, 1. Does anyone bother if I do this 1E minus 9? There we go, very tiny. It didn't work, whatever. V out. Huh, what happened? V switch. Oh, delay, 1 millisecond. There we go. There we go. Does that make sense what I just did? Okay, let me just show you. Our initial voltage, right, was 5 volts, okay? Does that make sense? Then I opened the switch, okay? Well, just imagine this was -1. This is right at there, okay? Actually, okay, let me just get rid of the delay. I'm gonna do one microsecond delay. We start at 5 volts and we're going down. What happens at 1 millisecond or whatever 1 is, okay? We go by 1, right? What's that voltage? It's going to be 1.81 volts, right? You see the slope? It's going down. You like that? It's an exponential and it's going down, okay? So I'm going to tell you another thing, and I don't know if the instructors are going to do this. I would. Is if you wanted to figure that's actually why I was hesitating for a second. Is you're going to realize that your equation is going to be dominated by this exponential, but what really matters is that term, okay? So there's another way that people like writing this. This is page 6. And that's if I have V out over T is equal to V in initial e to the minus T over tau, right? Where tau is equal to RC, correct? And my R is going to be 1K, right? Then my C is going to be 1 microfarad, right? Was that equal? What does that mean about my time? 10 to the third, right? Times 10 to the minus 6 is equal to 10 to the minus 3, which is equal to 1 millisecond, right? So after one time constant, right? If T is equal to the time constant, V out to tau is equal to VI e to the minus tau over tau, right? Which is equal to VI e to the minus 1. And can we compute that? VI times is going to be a number. This one's an important number. Calculator. Go scientific. Yeah, scientific. Where's E? Oh, I don't like this. Yeah, I'm clicking on it. It was letting me. Huh? This one? Oh. Yeah, okay. E to the, okay, let me just delete that. There we go. E to the power of -1. There we go. Is that what I want to show you? I think that's how I want to show you. Because by one time constant, what I'm trying to show you is, see, I don't know if I want that one. 1E. Let me see. E. No, I don't like this. I'm gonna go to MATLAB. So, you guys seen what MATLAB is? It's a calculator. And do the following. Enter. E divided by. Wait, E, no. Because this is 1. Hold up. I'm trying to think about what's going on. 1 divided by E. There we go. Exponent of 1 minus 1. There you go. 2 over 171. What I'm trying to show you is that this right here is one time constant. Does that make sense with everybody? So this is basically all I can tell you about the capacitors. There's more other equations you can do where, let me show you this. 7. Okay, 7. Bring this. You guys will be talking about this, I think, next week. Is what happens when I have the following. Plus, minus. Man, let me just put the switch on. V initial, V in, right? And then have some R, and I have some switch, all right? So this is basically where okay, I have a supply, I have a resistor, and then I have a capacitor that's filled to, I don't know, I'm gonna just say this is like 3 volts, all right? And this switch right here is at 5 volts, okay? So if I were to do the following, okay, if I were to close the switch, okay? And then if I were to do plus minus, right? And then you were to do V in minus IR minus the voltage over here, or the voltage drop, which is just this VI right here. Let me see how I want to do this. VC. Does that make sense? Putting C where VC, the capacitor, is going to be whatever is at V out minus 0, right? But initially I have 3 volts in there. That makes sense with everybody? But there's another thing I'm going to show you, and there's another proof for this on how to get a general equation on how to solve any of these problems, is where you have this I right here, right? I is equal to, what do you call it? V in, correct? Minus V out, right? Over R. Remember that good old equation? But then what? We have one I, correct? And this I is the same for the resistor and the capacitor. We can do this, C dVC over dt. Then you can solve for this general equation. Does that make sense with everybody? I'm going to do V out, and this is actually equal to C dV out for dt. Is that good with everybody? Because I think what the next thing that's going to happen is that I'll just run an equation. Let me get this set up for you guys. Save as exercise 5. I'm going to do the following. Just move this. Yeah, I don't like moving that. Go. I'm going to move this whole thing right here. Move. Boom. Stretch all this. Boom. Okay. Then I don't like this. Let me see. Boom. 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 This is V out. Boom. Boom. And I have some voltage right here. Okay. I don't like this. There you go. Boom, 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 boom. Put this to 5 volts. All right. And then okay. If I wanted to set this to 3 volts, right? This capacitor, right? I want to set this to some voltage. I put a V out right there, right? That's the voltage there, guaranteed. So I would change this right here to 3 volts. Okay? So then when you have a homework problem that says you have an initial charge on the capacitor, right? Okay? And then this right here, well, I'll just get rid of that for now. This right here is V in. Boom. Is that good with everybody? We just zoom the fit. So it's just the same circuit, okay? Same circuit. I have an R and I have a C, right? Okay? Actually, let me be more trivial. So, this is a bucket of water, right? And it's going to fill up to something, correct? When this is on forever, right? What's the voltage going to be at V out after infinite time? I have 5 volts, right? It's going to go into this. What's the voltage going to be? Okay, I think I got to go over one more fundamental before I leave today. V9. 9. Okay. 9. So let's just do this, plus minus 1 volt, all right? I have 1 volt right there, right? So a capacitor, I'll tell you one last thing. You see how we got parallel plates, correct? And these parallel plates, well, is the circuit connected in a way? Like wire-wise, actually, let me just do something funny. If I were to have a battery, right? Some 9-volt battery, and I have literal 2 plates, correct? Right? Actually, let me just do something simple. If this is 1 volt, right? And this is just a piece, just a metal, right? What's the voltage at this metal? Very trivial. What's the voltage? 1 volt, right? It's just a wire, right? Wire, 1 volt, right? Easy, correct? All right. So I'm going to put another plate over here. All right. And this is connected to ground, right? If this is 0 volts, correct? What's the voltage of this piece of metal? Metal 2. It's just 0 volts, correct? So what's the current in this circuit with this broken plate? There's like a gap. Gap. 0, right? There's no current, okay? It's an open circuit, all right? So eventually this is going to be 0 volts, this is going to be 1 volt. That's all a capacitor it is. It's just 2 plates. It's not connected together, okay? So that means with this volt, right, we have 1 volt, correct? After infinite time, right? What's the voltage going to be at the top plate? 1 volt, all right? So now let's just do the following. Let's just say I just boosted it up to, I don't know, 5 volts. Right? So, and actually this is the funny part, is initially, right, what's the voltage going to be when I go from 1 volt to 5 volts? It's going to be 1 volt. Okay, so let me tell you something about capacitors. Is capacitors, they don't like to change. Don't like change voltage. Okay, they don't like to change the voltage in there. It's a bucket of water. It's a literal bucket of water level. Okay, if right now it's at, like, let's just say 1 volt of water, right? 1 feet of water, 1 foot of water, right? And then I just have a hose, right? I'm gonna draw a house. Right? Hose, right? I just fill this bucket of water to 5 volts, correct? And then this right here is 5 volts. What are you going to see about the voltage? It's going to go up to 5 volts, correct? And then what happens after that? It just stays at 5 volts. Does that make sense? That's what capacitors are. They just fill water. And then what happens if I just switch this down to, like, what do you call it? Down to 0 volts. Then over time, you'll just see it go down to 0. You're going to be in our next classes and in your lectures, you're going to be describing how this changes, okay? Is it going to go crazy fast? Is it going to slow, etc.? All right? And you can change that rate by whatever resistance is in here, if I were to put a resistor. Good? Any other questions about this? Yeah, I know. I don't think they went too deep into the lectures, okay? I'm just giving you guys this head start so you guys have something to think about before you guys are surprised, okay? I'll be more prepared with what we can show you for next week, okay? Any other questions? All right, y'all. Guess I think that's about it. All right, have a good day, everybody.